Okay, so let's summarize what we've learned about definite integrals. Take plenty of notes on this. Left Riemann sum. Now, left Riemann sum, we know always starts with the initial value. So you can see here in the sums that we're adding up, we start with the first value and we end with one less than the last value. Okay, you can recognize this expression. This represents the change in x. And we see here we're using a Riemann sum, and the n represents the number of sums. Now, a right Riemann sum is very similar. Oops, I'm sorry, there's a typo here. This should be r of n. And so the difference between the left and the right is you'll notice that our initial point is not the first value given, but it's the second value. And with the right Riemann sum, we always end then with the last value. Again, it's the change in x times the value of the function and add it up together. Trapezoids, we've done plenty of those. Now for those, you'll notice a difference is we average the heights of the trapezoid. I'm sorry, usually we call it the bases. We average the bases or average the values of y and multiply those by our change in x. Now midpoint Riemann sum is usually quite challenging to calculate algebraically. And to be honest with you, we typically see it in a table form. So I have a table here. And let's say you were asked to calculate the integral from 0 to 60 of velocity using midpoint Riemann sum. Actually, they would tell you you're going to use 3 Riemann sums and it's going to be a midpoint. Now, with midpoint Riemann sum, you always use the value that's in the middle of the two given values. So I have to divide these 1, 2, 3, 4, 5, 6, 7 values into 3 Riemanns. So if I go from 0 to 25, this would be one sum. 25 to 35, that's a second sum. And then 35 to 60, that's a third sum. Notice how I divided those evenly amongst the rows. So the first sum, if it's midpoint, I look at the value at between 0 and 25, which is negative 30. So the change in x goes from 0 to 25, and the midpoint value of velocity is negative 30. Okay, now I do the second Riemann sum. I go from 25 to 35, so that change in x is 10, and then I look at the value in the middle, which is negative 14. And last of all, 35 to 60, that's a change in 25 for x, and that mid value is 0. So we can see that this value is going to come out as a negative value because velocity is negative in this scenario. Average value, that's what we learned today, integral over interval. Be sure to use units to help you guide, to make sure you've used the right formula to get the correct answer that you're actually looking for. Displacement. When you take the integral of velocity, it will always be your change in position. I would get used to thinking of it in that terms rather than thinking of it as distance, because it's only distance if velocity is positive the entire time. So if you think of it as change in position, you'll always be correct. Whereas here, you'll notice the difference is when we take the absolute of value of velocity, we do actually get the distance traveled. Now that's in the context of velocity. What if you have an integral of a rate that's not velocity? Well, it too will always just equal the change in value. Now the values will be different. It might be gallons per minute. It might be horses per hour. I don't know. But whatever the input is, that's your change in value. We talked about if a function is negative, then the value of the integral will also be negative. Now for these last 3, I want you to write in your own words, so I should see this in your OneNote, in your own words, what is the meaning of this? This is the definition of an integral. Describe it to me. How is this definition different? Describe it to me. And then describe how this definition is used. And last of all, here's a visual for the mean value theorem for definite integrals that we learned today in class. Great. I hope this resource page helps you.
You're so cute, honey.
Wait, I haven't stopped it.